How we doing this morning? Good. Just starting up the stream. Let's get the recordings going. All right. We're doing all right. Staying warm. No, we're not. We're not staying warm. It's very chilly here in Tallahassee. I'll tell you, also dry. Is it dry for anyone else? My goodness, I'm like moisturizing, I'm not a moisturizing guy, but I feel like I need an emergency response kit. You know, I'm like cracking up a storm with my hands here. Anyway, so stay dry. No, stay moist. Stay moist? Anyway, moisturize, friends. It's very cold here. I didn't come to Florida for this. Anyway, so a couple of orders of business for today. So a few reminders. Okay, let's get here. Today we are. Let's go on here. 26. So a couple of assignment reminders for today. Go to the 3rd of February. So we're picking project groups. Don't forget this, okay? If you're having a hard time finding a project group, grab someone after class if you're here. If not, you're like, I'm too shy, I can't find a project group. Submit a project group saying, please assign me a project group. As a last resort, please, okay? But you can always do that if really necessary, but please just make sure you get into a project group if you can, all right? Those are due today. Due today, Tuesday at 5 p.m. on Canvas. There should be a little Canvas assignment for you. Okay. And so for Friday, the idea is then for Friday, you have some project ideas. Okay. And I need to get you a document specifically outlining the exact requirements. I just got to upload that to Canvas. Thank you for your patience on that. But we've talked about it, right? You have to be able to simulate a dynamical system and then control it with techniques from the class. Okay. And now that you are all becoming experts from your homework in simulating dynamical systems, right? You should have an idea of what that entails. Okay, using ODE 4.5 or Euler's method, right, to integrate your dynamics, which are your differential equations. Remembering that homework 1 is due 5 p.m. Wednesday, tomorrow. Okay, hope you're all working on that. Okay, and because I feel like I gotta say it every time, coding-based assignments can lead to all kinds of challenges, and you don't want to be doing that at the last minute. So please get started. All right, we do have office hours Monday, Tuesday, Wednesday, and Thursday. I guess Thursday will be too late, but we've had office hours throughout. Okay, I had a couple takers. That's great. I feel like they've been helpful to the people who've come. You can also check out the homework FAQ page. Okay, again, just front page of Canvas. There's a big thing that says homework frequently asked questions, FAQ. Click on it, and it gives you hints to all kinds of stuff. And it also, for your animations, actually give you solutions to what the animations look like for part 2. If you go into the files page, there are videos. Okay, I had a few people ask, like, can they submit AVIs instead of MP4s? The reason we say we want MP4 files is because of file size is the big thing. So if you are trying for some reason having to submit an AVI file for your videos instead of MP4, make sure it's small enough, please. Okay, because the AVI versions tend to be huge, so compress it or something, but that's why we do that. So any questions on any of these 3 things, any of the orders of business here? None. Yes, 1. It's small file size, please, yeah. Because if you don't, so the reason I say this, so I gave you all the MATLAB commands in the video from last week, or from 2 weeks ago or whatever, right? Of how to do an animation, and I gave you the command that turns it into an MP4 format. If you don't do that, it becomes an uncompressed AVI, which is enormous. You won't be able to submit it. But if you know how to compress videos, that's fine. Well, hopefully, please we'll find if it gets a codec that we can read. That's always a danger with AVI files, is that you don't have a codec on your computer for it. MP4 is more common. All right, other questions? All right. So, what's the name of this course, friends? Anyone want to remember? Does anyone remember what this course is called? Applied Optimal Control. Okay. So today, we got Applied Optimal Control. We've spent so much of our time, friends, talking about the control, which required us to introduce dynamical systems. You know, there's differential equations we have to integrate and therefore simulate. And we added a little control input, and we added a little feedback controller. And for your homework, you're adding a feedback controller and a feed-forward controller to your system, right? So you're getting some background in control. And many of you have seen a lot of that stuff before in a controls course. But many of you have not seen a lot about optimality or optimization, okay? So that's what we're gonna bridge into. That this is our introduction to optimization. Let me give you a little tease of this in the very first lecture, okay? So optimization is the process of finding a best decision given a scenario or constraints. That's generally speaking. There are lots of ways you could write this out, but that's the idea. You're trying to find the best thing. Optimization is like the science of finding the best. All right? So optimization, the process of finding the best, doesn't necessarily mean you will find it, but it's the process of finding it, right? What's the word optimal mean? Anybody? The best. Optimal is the best, okay? So an optimization is the process of finding the best, right? So theoretically, optimal control, that's the best control. We all love the best. You know, that's great. Best control. Now, a lot of times, perfectly fine is good enough. But there's something beautiful that if you can define what you want, that defines what the best is, and we now have a process to get that, that's like automation. It's automatic. It's almost thoughtless. You get you an answer to what you need, right? So there's lots of ways you could define, for instance, a controller. You know, we did this in our lectures, right? In our coding lectures, we put proportional derivative controllers on our pendulums, right? Who says that proportional derivative controllers are the best? I don't know. I do. I'm the professor. I don't know. But I just decided, hey, let's put a proportional derivative controller on there, right? Because it's something I know. And then we chose those little k values on the proportional derivative controller. What were those called? Those k's. Gains, right? Who chose that gains? We did. We chose those gains. Are those the best gains? Who knows? Best depends upon what, you know? But wouldn't it be nice if we decided what the best is and then out popped the controller? Oh, isn't that lovely? And not just control for anything, right? For any decision. You know, go to a restaurant. You want to order some food. Well, what do you want? You might know off the top of your head what you want. Or you might know what you like about food. Then you look at the menu. Like, I like spicy things. I'll go to the spicy things. Okay, I like food that's spicy. So, okay, I'll search the menu for things that are spicy. And then I will find the spicy thing, and I will order the spicy thing and regret it the next morning. Okay? Right? So there is a beauty in defining what you in defining the problem in terms of what you want. I mean, you're all engineers, right? Who here's in senior design? You have things like customer requirements, right? You know, you're meeting with your senior design senior design people, or you're meeting with Dr. McConomy, right? You're all in Dr. McConomy's class, right? Does Dr. McConomy tell you exactly what to build? Can you do it? No, you don't. You spend a lot of time figuring out requirements. And then those requirements dictate what you actually build. You look through options, and then you actually build those things, right? So that's the beauty of optimal control. You define what you want, and the controller should come out, all right? So optimization has three major components, all right? So see, three key components. Oh, we're having some real drop frame issues, aren't we? Oh, okay. Unfortunate. We'll upload another version. Three key components of optimization. Got your cost function. Sorry, I'll go in the opposite direction. I'm sorry, I'm distracted by that. So we have your decision variables. These are the decisions that you make. This is of optimization. All right. Optimizations. Decision variables. You have your cost function, and you have your constraints. All right? If you can define what you want to do in terms of these three things, you have an optimization problem that you can then attempt to solve. And by attempting to solve it, hopefully gives you a decision that you want, right? So in the context of going to the restaurant, your decision variables, one decision variable might be the thing you're ordering on the menu. Pretty simple one, right? You know, if it's a drive-through restaurant, you might have another decision, which is like large, medium, small. Supersize. And supersize doesn't exist anymore, right? They killed that and just called it large. Okay, different times. Okay, so decision variables are three variables to be chosen and changed by an optimization. Okay? And you might have these decision variables. They might be W1, W2, ... up to some Wn. Okay? Those are your decision variables. In this class, we will almost always be making these decision variables real numbers. Okay? Just by default. So if I don't lay out the fact that it's a real number, assume it's a real number. That there are many kinds of optimizations that have not real numbers, where you have integers. They have to be 1 or 2. You know what integers are, but like that is actually a major change to how optimizations work. And so it actually makes your problem sometimes easier, sometimes much harder. Okay? And in control, one of the reasons we care a lot about real numbers is because we're often making a decision like how much do I open the valve on my power plant? 50%, 75%, that's a real number. Not always just open, close. And a lot of times in motors, right? Your motor isn't just on or off. I want to send 2 amps of current to my motor. That's a real number. It could be 1.9 or 1.95. We want to give it that freedom. So another way to write these, you have a whole list of numbers. What's a convenient way to write a whole list of numbers in math, in linear algebra? As a vector, right? So we have a vector W column vector, W1, W2, all the way up to Wn. Okay? A lot of people might write a little bar above it. I know we've been writing bars above our vectors. It's just understand when you see the W by itself in this context, it's a vector. Okay? A vector of decision variables we call a decision vector. Creatively enough. It's a list of all your decisions you have to make, right? Now, in the context of, say, our controllers our feedback controllers that we wrote in our coding lectures, what were those numbers that we were choosing in the controller? What were they called? Gains, thank you. I was being a little vague. Gains, right? In an optimization, you can make those gains decisions, right? Put them in an optimization problem. What are the things we want to choose? That's the decision vector. Okay? Now you have the cost function. Okay? If you're in my machine learning class, same idea of a cost function. All right? So, is a vector valued function, scalar valued, gosh, goodness, one of those mornings. I blame the cold. The scalar valued function of decision variables that is optimal when minimized. Okay? We'll call it some f of w. Okay? So it's kind of intuitive. If you put in a w, it gives you a big number. High cost is bad. If it gives you a small number, low cost is good. That's easy. So if you just get into the habit of framing your decisions in your mind as a cost function, high number is bad, low number is good, that's your cost function. Okay. So imagine we're at a restaurant again. Okay, our cost function could be about how good the food tastes. So you might say, well, goodness tasting of food, we want goodness to be high. So if we want it to be a cost function, our cost function will be negative goodness. Because we want a large goodness, we want that to be a large negative value in our cost function, right? That makes sense? Low is good, high is bad. You can see this, people will call this different terms in the optimization literature. Objective function is literally the same thing. It's just a bit of a counterintuitive phrase because like cost, low objective is good, but that's counterintuitive to say, so I stopped using objective function. Some people use loss function because high loss is bad, right? But low loss is good. It's the opposite of reward. Reward, high is good, low is bad. Anyway, but we will use cost function in this course. But if you see the phrase objective or loss somewhere, that's what it is. Okay? Then finally, you have your constraints. Constraints are a vector valued function and by the way, when I said scalar valued, meaning it returns one number about the cost. You need one number that says how good it is. I use this analogy every once in a while. There's the movie Moneyball. Has anyone heard the movie Moneyball? People are alive from Moneyball. Okay, kind of, maybe not. It's about baseball sport. It's about baseball. Brad Pitt is in it. Okay, Jonah Hill is in it. Jonah Hill? Yes, Jonah Hill. Yeah, and they're all about trade. They're trying to find the optimal way to trade players for baseball teams. okay? And they had to take these players with all these different skills and they have to combine it into just one number, okay? Like, oh, how good do they get on base versus how well do they do this? They combine it somehow into one number. And you can think of that as a cost function, right? That it's all about getting it down to one number, reducing people to just one number. Don't do that in real life. But apparently in optimization, you have to reduce things to one number. So constraints are a vector valued function indicating conditions that must be true of a viable solution. Okay? A little bit of a weird way to say it. These things have to be true. And you can fit these things into a function. For instance, we have constraints on maybe what we buy at the restaurant. You only have so much money in your wallet. That's a constraint. You can't pay more than that. Okay? All right? So that must be, so whatever decision you make must be within those constraints. Okay? And constraints can be much more complicated than that. All right? But you can always put them in the form of G of W is less than or equal to 0, where G returns a vector and 0 is a vector. So if you could have, because you could have many constraints. Okay. It returns a vector. So you could say that, hey, I need to, for instance, like at a restaurant, you could say I have only so much money to spend, or I only want to eat so many calories. You could just keep adding on constraints, add them. And if you have all, and if you add another constraint, what do? You just add another row to this vector. Okay? And you add another row to this 0. And you're like, my friend, it always has to be less than or equal to 0? That seems restrictive. Okay? What if also I want something to be, instead of an inequality, an equality? Can't I do that? Yes, you can. Okay? Let's say I want to spend exactly $10 for some reason. I have that particular compulsion. I want to spend exactly $10 at a restaurant. I must spend exactly that amount. So the amount I spend, let's just call it, the price of the thing, I could say is less than or equal to 10, and it's greater than or equal to 10, right? What value does it have to be? 10. You can write this is an inequality constraint. But any equality constraint can also be rendered into two inequality constraints. There's two inequalities. Okay? There's two inequalities. For instance, if you have some W is less than or equal to 10 and W is greater than or equal to 10, it must be 10. Right? And you notice that it's a less than or equal to. How do you flip the sign? If you want a greater than or equal to, how do you flip the sign? You multiply it by a negative number. 1 is my favorite number, though the loneliest. Okay? So if you want W is greater than or equal to 10 to be a less than or equal to, what do? You multiply both sides by -1, right? And then you get minus W is less than or equal to -10. And now it's all of a sudden a less than or equal to. So that means our G of W, that's not a G at all. G with back problems. Okay. You get some G of W as an example. Okay. is you could say that it needs to be less than or equal to 0, right? That means that we would want W minus 10 is less than or equal to 0. And let me move this aside here. It's in the way. Wow. 1W equals 10. And I can move this over here. Minus W plus 10 is less than or equal to 0. We're following this high-level algebra. We're doing okay this morning. It's early. Take it easy on you all, okay? That means you have W minus 10 in here, minus W plus 10. I've written those both constraints as a vector-valued function. Hopefully, I've demystified that a little bit for you. Question? In this case, I've made them the same, right? But they could be different. Depends on the constraint that you want, Marco. What do you want? I don't need to know right now. You tell me later. Okay. Right. The three things: decisions, cost, constraint. With that in mind, let's write an optimization problem. One of my favorites, okay? Call it the fencing problem. So, where the idea is that you are a farmer, okay? And you have land that you want to fence in, okay? You're going to create a rectangular fence, my friends. So you're going to, we're going to build a rectangular fence. Where you got some length and then some height of the fence, okay? And you have a total amount of fence that you have. Let's just say you have 40 meters of fence. You're a metric farmer, okay? 40 meters of fence. It must be a rectangle, okay? How do you write an optimization problem? That maximizes the area enclosed. Okay, simple one, right? So writing an optimization problem, what three components do we need? Number one, decision variables. What are our decisions in this problem? Length and height. Thank you, Christian. You seem bored. I'll try to add some more fancy math. Okay, yeah, all right. I mean that in a good way. It means you're like, oh, this is, you all are like, yeah, this is easy. I know how to write this optimization problem, but it's length and height. And we're going to put them in a decision vector, W, with a length and a height. That's our decision vector. Okay? What about our cost function, friends? Cost function is going to be some function of our decisions. This is where we start thinking about our problem. We want the cost function, when it's minimized, to be the best. What do we want to be the best as possible? Area. Okay. Well, what's the area? In length times height. Are we done? Are we done? Is that the cost function? Let's minimize that. Yeah, because if we were to minimize that, it would try to minimize the area. And you know what? The optimization will be dastardly sometimes. It'll try to minimize it as far as it goes down to minus infinity if you want to, right? It's tricky. So we don't want to minimize area, we want to maximize it. So I heard in the audience, minus L times H. That negative maximizes. And this, of course, is the area. All right? As our cost function. What about our constraints? So I'm going to write them as g of w. If you're fancy, you put a bar above it because it's a vector value function, but we'll deal with that later. What are our constraints? Let me put it on a new line. Anybody? In plain English. Yeah. 2L plus 2H is less than or equal to 40 meters. It's our perimeter limit, right? So 2L plus 2H is less than or equal to 40. Now we want to put this in the form of g of w is less than or equal to 0. So we just got to take that 40, move it on the other side, right? So that means it's going to be 2. That means that g of w is going to be 2L plus 2H minus 40. That's less than or equal to 0, right? 2L plus 2H minus 40, less than or equal to 0. We follow that math? Sure we do. I ask facetiously. Okay. We did it, I think. Anything else? So L and H, by default, they can be any real number, right? This is where our friends' optimizations can be a little tricky. We're trying to maximize area, okay? And by the way, does anyone know the solution to this problem? Off the top of their head, what's the answer for the best? For square. Okay, 10 by 10 square, right? Okay. But I'll tell you, optimizations are tricky. They can think of solutions you might not have thought of. Let me give you a better answer according to this optimization problem we just wrote, right? What are the rules? It's trying to maximize area while trying to keep this constraint obeyed, okay? I'm going to give you an answer. Let's try L is equal to minus 1 billion and W is equal to minus 1 billion. Does it satisfy my constraints? Well, 2L, so that's 2 minus a billion, so it's minus 2 billion, minus another 2 billion, so 4 billion, minus 40, of course. Is that less than 0? Yeah. All right. What's negative a billion times a negative a billion? Positive a billion. Negative a billion, sorry, positive 10 to the 18th. What is that? Anyway, that's a big negative number. I beat you. I beat you all. And optimization can figure out that answer, right? Optimization, you got to be careful. It's like a magic genie. You got to be careful what you wish for. Just might get it. So we actually need more constraints, don't we? Because we know we can't have negative fencing. In this case, negative fencing is the right, according to this, the right answer. Look how clever I am. Beat you all. So let's add more constraints, right? So we need, so we're going to say it's a must have, we must have positive L and H, right? Which means that L must be greater than or equal to 0. H is greater than or equal to 0. For those of you worried about that, but the equal sign in there, don't worry about it, okay? All right, so we have to write this in terms of things being less than or equal to 0. So what do? We have to multiply both of these by -1, right? Times -1 times -1 If we do that, that becomes minus L, excuse me, minus L is less than or equal to 0, and minus H is less than or equal to 0. These are two new constraints. We throw them into our constraint vector. So now our constraint vector is G of W has our perimeter limit minus L and minus H, and they're all less than or equal to 0, right? Here's the thing. So much of optimization, as we will do in this class, once we have these equations, we're done. We can literally take this function, put it into an optimizer in MATLAB, and the cost function, and the decision variables, and MATLAB will try to give us an answer. There's excellent optimization algorithms out there that are already coded up for you to use. Okay? So much of this class is writing the question down correctly so a piece of code can solve it, an optimization problem, an optimization solver, I should say. Okay? Any questions so far? We wrote down the fencing problem. Okay. Now, how do we solve the fencing problem? Okay? It's slightly more tricky. I'm going to reframe it ever so slightly. Okay? So let's solve the fencing problem. Okay? But that requires us to know how we know we're at a minimum. Okay? So that takes us into the process of types of minima okay? There are two types of minima of a function, because we're trying to find a minimum of a cost function, right? Okay? There's local minima and global minima. Okay? If I have some function, some cost function, f of w, say it looks like this, what's the absolute minimum, the lowest value? It's this one here, right? That's the global minimum. Minima. There we go. And this one here, it's not the absolute bottom, but nearby, everything around it, it's lower than, right? So locally, it's a minima, so we call it the local minima. Okay? Obviously, it would be great to find a global minima. They're better, right? By definition, they're lower on the cost function, they're better. They're also harder to find, okay? Theoretically, they can be harder to find, all right? So global minima, are better, but typically harder to find. Okay? A common way that, so as a result, like finding local minima is much easier. There's a couple of conditions that you can write down that tell you if you're at a global minima, okay? So, or a local minima. So local minima, so you can define a local minima via the following mathematical conditions. Mathematical conditions. Now, we know intuitively from calculus, how do you know you're at a local minima, friends? Second derivative and also the first derivative, right? The first derivative has to be 0, it has to be flat. The second derivative tells you if it's concave up, right? It's that exact, those are the exact conditions, just written maybe slightly more fancifully than you're used to seeing, okay? The fact that the first derivative, so the slope at that point must be 0, that's the first derivative, the first order derivative. So we call them the first order necessary conditions. Conditions. Specifically that the partial derivative of f, your cost function, with respect to your decision variables equals 0. Okay? Now keeping in mind that you are taking the derivative of a scalar with respect to a potential vector of decision variables, so this can be a vector, meaning that all those partial derivatives must be zeros. So I'll just write that off to the side real quickly. That would mean that partial f partial w1, then partial f partial w2, all the way up to partial f partial wn. Each of those must be equal to 0. So every decision, no matter which way you move it around, it doesn't get any better, right? Okay. The first order necessary conditions. And once you have hit that necessarily it must be flat, then you check, is it concave up? Is the bowl shaped up? So you call that the second order. You call those the second order, is the second derivative. Second order sufficiency conditions. Okay, so first you need this, second you need that. That's the second derivative of f of w. With respect to your decision variable. And it needs to be positive, so we say it's greater than or equal to 0, right? All right, you learned that in the context of where w is a single variable. There's a single variable that you're trying to figure out. So is it flat at that point? And is it a bowl at that point? Is this number greater than 0? However, if this w is a vector, it just gets a little bit more complicated. Here, we had this, and this is functionally what we call the gradient, right? You learned that from Calc 3 or multivariable calculus. This second derivative is called a Hessian, H-E-S-S-I-A-N, Hessian. So when you have multiple decisions, this becomes a matrix. Okay, we have partial squared f partial w1 to the second. Then you've got partial f squared partial w1 partial w2. One of these days, I'm not going to bracket these things first. I'm going to make the brackets at the end. See how much space you need, then you bracket it. I will never learn that, DJ. Look at that. Look at that smile. He knows. I've been doing this for years. I do it. Okay, fine. Making me feel better. Thank you, DJ. All right. So partial F, partial W1, partial Wn. Okay, then the next row. Partial squared F, partial W2, partial W1. It's getting small. I'm going to make it bigger here. So unclean. Ugh. I love everything about the iPad, except my handwriting is way worse on the iPad. Okay. Then you have partial, second partial of F, partial W2 twice. You have partial F, partial W2, partial Wn. Hopefully you see the pattern emerging. In the first row, this W1 is always the same. And the second one increments, right? 1, 2, 3, N, right? Then for the second one, you have W1. So this is constant, W1, 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 right? Okay. For those of you who learned about we learned about Jacobians. Very similar to a Jacobian, but there's key difference, okay? So looks very similar. Then all the way down, you kind of scroll down, you got partial, all the way down to your nth row. So partial Wn squared. Then you have partial F squared, partial, oh, sorry, this is W, oh my God, I'm so silly. W1, no, Wn, W1, I'm sorry. Sorry. There you go. Nth row, Wn. First column, W1. Nth row, Wn. Second column, W2. All right, and then all the way out to the nth row and nth column. So it's going to be partial Wn, Wn squared. That's what the Hessian looks like. Okay. Now, unlike the Jacobian, which does not have to be square, this is always square, right? You see the n there, you see the n there. It's always going to be square. Also, my friends, if I take the derivative of a function with respect to W1 and then W2, how does that compare if I take that same derivative, except I take it W2 and then W1? Reverse the order of the derivatives. How much does that matter? Not at all. Not at all. It doesn't matter. So these two numbers are going to be the same, right? In fact, here this is the diagonal of the matrix. Everything is across the diagonal is going to be reflected. They're going to be exactly the same, right? So it's a symmetric matrix is what we call it. Square and symmetric. Okay? Make sense? So, if we have these, any questions? That's what Hessian is. Why did I go through that trouble? Well, of course, it's the second order sufficiency conditions. It tells us we're actually at a minimum, as opposed to just a maximum or a critical point or a saddle point or things like that. Okay? Well, we have these mathematical conditions. You'll notice, though, it doesn't, in no way it takes into account the constraints. Okay? Constraints add some trickiness. So they do not, so the conditions do not account for constraints. Okay? Constraints add a little bit of trickiness. We'll solve that in a simple way today. Okay? So let's give an example. Let's solve the fencing problem. Because now we have these conditions. We can try them. We can actually say, hey, if we have, so back to fencing. Back to the fence. We have our cost function. f of w is equal to minus length times height, right? Is that it? Yeah. Sometimes I throw in w for width, and I regret it because we already have a w. Okay. All right, we got L, length and height, right? We also have our constraints. Right now it's an inequality constraint. I'm just going to magically turn it into an equality constraint because equality constraints are going to be easier to solve by hand, and you'll see why. Okay? So I'm going to say that our constraint is that 2L plus 2H is equal to 40. We must use all 40 perimeter meters of fencing. In our heart of hearts, we know that's the right answer anyway. Ask yourself, you knew that, right? Don't not use the fence. All right? So what we could do is with this equality constraint, we could solve for either L or H and then substitute it into the cost function. And as a result, we have no more constraints. We have gotten rid of them. And no longer do we need to say it's going to be a positive number. Well, we're just going to ignore that, and it's going to be fine. Trust me. All right, so we're going to solve for H. And to be clear, it's not the same as the Hessian, which we will eventually call H. Sorry. All right, solve for H. So that's going to be, H is going to be equal to 20 minus L. I skipped an algebraic step. We're going to substitute in. So now the f of w is going to be equal to minus L times H, which is equal to minus L times 20 minus L. Okay, going to distribute that. So f of w is going to be equal to minus 20 L plus L squared. Now, what's our first order necessary condition? First order, that's what func is. It's that the partial derivative of f of w with respect to w equals 0. Okay? Now, our w, our decision vector, is length and height. So if I take, and so therefore this partial derivative is going to be partial f of w partial L and partial f of w partial h. Notice I've gotten rid of h. So this second one here, partial derivative of this with respect to h, I see no h's. Do you? I don't see no h's. Okay. 0. Now, partial derivative of this with respect to L is going to be minus 20 plus 2L. Okay? And what does this have to equal? These both must equal 0. Well, I'm glad to say, friends, that 0 already equals 0. Whew. That one's easy. Therefore, this must equal 0. So minus 20 plus 2L must equal 0. Therefore, L equals 10. And if H is going to equal 20 minus L, therefore H equals 10. The square. We solved that by hand. The way we did it is by substituting the constraints in order to make our decision, in order to get them, basically substituted the constraints away, right? You can't always do that, right? Now, that said, we did not check the second order sufficiency conditions, did we? We don't know if this is a maximum or a minimum. So let's do the second order sufficiency conditions. SASC. Partial squared f of w, partial w squared. So it's going to be partial f, which is, let me just write f down here because it's way up above. So it's going to be f of w is equal to what? 20 minus 20L plus L squared. Okay. If W is L and H, That means that this first is partial squared f partial L squared. This is going to be partial squared f partial L partial h, partial squared f partial h partial L, and partial squared f partial h squared. Okay? Okay. There are no h's in this, so anything that has a partial h is going to be what, friends? 0. It's going to be 0, 0, 0. And this is going to be the second derivative with respect to L. That's just going to leave the number 2. Okay? All right? Now, how is you know if a matrix is greater than 0? This is a linear algebra trick question, in a way. You have to know that, so technically, if this was just, we could simplify this one problem just to this one decision that we're making, L, right? That's greater than or equal to 0, we would agree. It's going to be, it is satisfied. Okay, this is a minimum, all right? But in general, if you have a matrix, you don't check if it's greater than or equal to 0 by just checking every entry and saying it's greater than 0. No, that's lame. That's not how linear algebra works. That makes way too much sense. In fact, very smart people said it's much more meaningful to say that the matrix must be positive definite. Definite. Okay? Meaning that all eigenvalues of the Hessian must have positive real parts. So what that means in actuality, so if we go back up to our bowl that we were talking, like the little bowl, if we know we're at the bottom of the bowl, if it's just a plot with one variable in, one variable out, we know it looks like a bowl like this. If we have two variables going in, suddenly it looks like a conical bowl, right? If you have 3 dimensions, all you have this like hyperdimensional bowl, right? How do you define this hyperdimensional bowl? It's hard to do intuitively, but we have linear algebra to help with that. Okay? Basically, if this thing is it makes sure that it's not a bowl in one direction and like a ski slope in another direction. Okay? It can look like a saddle if you don't check all of these eigenvalues, right? Okay? So in this case, we have solved the problem. Now, technically, as mathematicians might point out, that it's not positive. This is positive semi-definite because this one's a 0, but we're going to let that slide for today. But the point is, we computed a Hessian, computed a gradient. And if we set the condition that the gradient must equal 0, we can solve, in some cases, for what the optimal value is, right? In this case, it was a square. There are other ways to include constraints that we won't cover today, and be able to set up the conditions, the first order necessary conditions, okay? They're called the KKT conditions, all right? We have not gotten to, I'll just write this off to the side here. That's a little bit more complicated, but honestly, not as complicated as you might think for constrained optimization problems, where you don't, straight optimizations, where you don't have to substitute in the constraints to turn it into an unconstrained optimization problem. So constrained optimization problems have constraints. Unconstrained problems don't have constraints. Does that make sense to people? Do I have to write that down? Or are we good with that? I think we're good with that. Okay. All right. So, but again, this tells us if we have a local minima, right? How do we know that's the global minima? Well, we might not know. from this one condition, right? It only tells us if that one solution is a bowl up. Could there be one all the way over there that's way better, right? Well, I'll tell you, one way to know that there isn't is the fact that no matter what value of L or H I put in here, that value is always positive, right? That concavity is always pointed up, no matter what value of L I put in there. So we'll think about what that means in the physical space, okay, of like this cost function, right? Imagine you knew it was concave up everywhere. That means it's always accelerating. Can there possibly be any nooks and crannies to get caught in with your local minima? No. There are none. Right? Doesn't that make sense? If I'm going to have some kind of cool curve like this, right? Whoa. If it's going to change like that, at some point there are inflection points that change the sign of the second derivative. And when I took that second derivative, there's no decision variables left. No decision I make will change that concavity. So I know for a fact that I've not only found the local minima, there is no global minima anywhere else that'll do better. Does that make sense? And that's just one example. Okay? There's an entire class of optimization problems that you can people have figured out. Not just this one, okay? Not just this one, where the local minima is the global minima, or there is no better solution than that local minima you found. Okay? And those are called convex optimizations. Okay? Entire class of problems, and they are amazing, okay? Because finding local minima, we've agreed, is easier than finding a global minima, probably, right? So if you are confident that your problem, that the local minima is the global minima, your life's easy finding that solution. In fact, we have very fast algorithms for finding that solution, okay? No matter how, and it scales really, really well to many decisions, okay? We'll get to why. So, but first let's define convex optimization. So a convex optimization, and one thing I'm going to put in here without hopefully confusing you all, is the word program. Programs, okay? Or programs are optimization problems where a local minima is as good as the global minima. This is a somewhat intuitive definition for what can be a fairly complex topic, okay? And if you were to imagine what it looks like, it might look like this, right? Let's look at that parabola. Let's say it's a parabola, right? If we know it's a parabola, then we know that that's the bottom, and there's no other local minima. That's a classic example. So if I find that local minima, I know it's as good as the global. It can include constraints as well, which is another cool wrinkle, okay? So imagine, my friends, that this is my cost function, right? But I also added a constraint that said that my W cannot be less than this number. All of this is off limits, right? I can't go there, not allowed. Okay? If I find the locally lowest value, which is that's allowed, which is right here, guess what? It's still the global minima. Okay? If I can draw a constraint that looks like a line, these problems are still convex. The local minima is still as good as the global minima. Now, you will note that technically speaking, it's not flat at that curve. Like I said, the first order necessary conditions change a bit when there's constraints. But it's still, that's the best solution we can find anywhere. Okay? And that's incredible because that scales to not just one decision, but as many as you want. Okay? In fact, let's see if I can do this real quick. Just to whet your appetite. So I'm actually going to pull up MATLAB. See, hopefully this works today. How's this working? All right. Oh, actually, you can't see it, so let me project that for you all. I apologize. Ba-ba. See that? See the MATLAB? Did you hear me still? No, I just came off. Yeah, probably just came off of the audio for a second there. That's MATLAB. We've seen this before, right? Yes, we're all very excited. No one is asleep. I'm glad to see it. All right. So I, my friends, have created a convex program. Don't worry about the code. It looks fancy right now. But I'm going to create a convex program that has 10 variables. Okay? And actually, the way I know it's convex is because the Hessian is always positive definite. Okay? And I'm going to use a built-in MATLAB solver to find the optimal solution for 10 variables. Okay? It's randomly generated. Okay? I don't know anything about the problem other than the fact that it's convex and it's got 10 variables. Okay? And I'm going to have MATLAB solve it. Okay? So MATLAB is going to search for the best solution across not just one variable, which would be on a number line, or two variables, which would be on a grid, or three variables, which would be a volume, but 10 variables, which is, I don't know, a hyperspace dimension. I don't know. It's going to search that to find the best possible answer. Okay? And it can do this with constraints too. I'm just not on the constraints on right now. Okay? And it's going to search that. So it's a huge space. I mean, think about that. You have, imagine you're like counting numbers along one number line. Let's say you have n of them, right? If you have one dimension, there's n of them. 2 dimensions, that's n squared. 3 dimensions, n cubed. 10 dimensions, n tenth. That's a lot, right? It becomes so huge and scary. Computer scientists call this the curse of dimensionality. That the more decisions you add, you are cursed with so many options and combinations of options, right? But if your problem is convex, how long does it take to solve? Well, I'm glad you asked. The answer is 7 milliseconds. 4 milliseconds. That's pretty fast. I'm going to add more variables. Right now, n equals 100 variables. 5 milliseconds. Pretty good, right? This is my laptop. I'm not running this on a supercomputer somewhere. Let's say I have 1,000 decisions. Yeah, 26 milliseconds. Pretty fast, right? 1,000 decisions being made that quickly. Think about the power of that. Imagine that you've turned a control problem into a convex optimization. That means that you can set up your optimization problem. You could say, I want my robot to go there. I want my power plant to optimize my power, but my conditions have changed. I would change the optimization problem and get an answer of what to do in milliseconds. That's incredibly powerful. When I've showed you back early in the class these drones, remember this like drone that was flying around? You have like a thing coming at the drone, right? It was solving a convex program on the fly. It would say, here's where the obstacle is, here's where I am, these are my dynamics. What decision do I make? We turned it into a convex program, solved it in milliseconds, and that gave it a decision. We use that decision for a few milliseconds and say, oh, hey, what's the situation now? Change situation. Get a new answer, right? This is what we'll be doing on Thursday. We will be showing you how to use these tools, okay? All right? Hope that whets someone's appetite for how powerful convex programs are. All right? So, what are some examples of convex programs, okay? When I say programs, I apologize. In the context of this class, program means optimization. Why? It's historical, okay? Before there was computer programming, as we know it today, mathematicians called optimization problems programs, and the name has stuck, okay? Even though most people don't, when they say program, they don't just assume you mean optimization. So I will try to use the phrase optimization, but you will look in the literature online, and you'll see people talk about convex programs, and it just means optimization. No one can see what I am doing. The whole time I was just beautiful, and you couldn't even see that. Wait, no, you saw this part, right? Good. That's my favorite drawing. I'm glad. Whose fault is that? Let's get this here. Yeah, I got to change you guys. Now you can see it. This is not hard at all for me to do. Okay, right. So my beautiful drawing, my favorite drawing. You see it, right? All right. So there are two. There are conditions. So if you can set up your optimization problem in a way that is convex, your life is so much easier. Okay. So you can give it to a solver with constraints, and it will also solve it. Okay. So we'll talk about two quick types. Okay. There are some classes. So types of convex programs. And again, programs means what, friends? Optimization, right? So I say program, I mean optimization in this class, okay? Types of convex programs. It will be called a linear program, okay? Okay. Where your cost function is a linear function of your decision vector, W, meaning it's a constant times W1 plus a constant times W2, or whatever you're calling your decision variables, right? And your constraints are linear. In W, linear functions of W, right? If your cost is linear, your constraints are linear, congratulations, it's a linear program. It's convex. Your life is easy. You can go into MATLAB, you can type in your linear programming solver to solve the problem, give you the best answer. It's called linprog, the linear program. How creative. There's a quadratic program. That's where we'll stop with today, where your cost is quadratic in W, but your constraints are still linear. And it's convex if the Hessian of f of W is positive definite. And that's what I generated in my MATLAB code, positive definite. I just had a little piece of code that generated a random positive definite Hessian of a giant size. I'd solve. and we'll show you some examples on Thursday. All right? Good luck finishing up the homework, okay? Have a great day.